Okay, let's start. Okay, so this time, to save time, I prepare. So this is scanned. Uh, so from the whiteboard, so I write the key steps. So the key material I will talk about on the whiteboard and just scan the document. So maybe later we can try to do this more efficient way. So I write not the full details, but the sketch of the materials I will talk about in the lecture. So this will be more effective, will be more fast, right? And I can still add comments on the app. So some students suggest me like to go spend one more lecture on Markov chain. So this is section 5.6 on asymptotic behavior of Markov chains. So yeah, I will spend one more lecture on this. So from next class, we will skip the ergodic theory and just start the construction and the basic properties of Brownian motion. Okay, so this today we will talk about asymptotic behavior of Markov chain. So what is asymptotic behavior? So it basically means we want to know if we send this Pn, right? So Pn, so which gives you give x0 equals to x, right? We want to compute the probability and n step equal to y, right? If you send the n goes to infinity, can we say something about Pn xy? So if we know this, right, we know Pn xy, right, we can compute the n step probability distribution, right? So y, so we know, like, give you an initial probability, right? If you time the transition probability matrix of just the transition probability. So this is 0, you get mu1, right? So if you iterate this, you get p0, p to power n, you get the distribution and n step. Okay, so if we know the limit behavior or asymptotic behavior of this, right? So then we can compute mu n, right? So this will give, if you know the information about Pn, the asymptotic behavior of Pn, we can compute the n step. We can approximate n step distribution, n step distribution, which is mu1, right? Distribution. Okay. The idea is very simple, right? So if the case one, so if y is transient, right? We can easily get the limit is just 0, right? And then goes to infinity. No matter what x you choose, right? You always get 0. You always get 0. This is very easy, right? Because y is transient, right? Which means rho yy is 1. In this case, from the theory, right, in the recurrence and the section, so we know this is finite. So we're starting at x, and you just compute expectation or average average number of visits to y. So you can show this is finite. Right? To be more precise, actually, this is just we can write the explicit formula rho yy n minus 1. So this is just rho xy 1 minus rho yy. This is finite. So since this is finite, right, the sum is finite, right? So we know each term will go to 0. Right? So if y is transient, right? So this question is trivial. So from now, we just focused on the case y is recurrent. Okay, so if y is recurrent, is not trivial, right? So to do that, so you can guess, right? You can guess from a very easy example. You can guess what's the limit it is, right? What's the limit it is? So you can compute, right? So you can compute an example. You can compute a very easy example. So which is what I call, right, the weather model, right? So if it's raining, right, it will stay raining. So I've got the basic interpretation, but you can think the transition probability given by this. And you can really compute Pn. So you can really compute Pn. This is just the nth power of the matrix P. This is a basic linear algebra problem, right? So actually you can show this converge to mu 0, pi mu, pi 0, pi 1, pi 0, pi 1. Is given by the stationary distribution. Stationary distribution. And in this case, right, we know Pn x y, right? So it just converges to pi y as n goes to infinity, right? This is a weather model we used in the very beginning as motivation. Okay, but we want to treat a general setting, right? So from now on, let's define right? This is a theory we want to, in the end, we want to prove this type of theory, right? So under certain assumptions, so Pn x y will converge to the distribution, the stationary distribution. And this really doesn't depend on which x you choose, right? So it's kind of, as n goes to infinity, your initial point, your initial memory does not matter, right? You lose the memory of your initial state as n goes to infinity. So before that, let's see a basic, very basic fact. It's about is very similar, right? It's a very baby model of recurrent or ergodic type theory. So to do that, let's define NNY. So this is the total number of visits of Y. N. So we just counting this N, or this random variable, counting how many visits to Y up to time N, right? So yeah, so this is different to this, right? So ny is kind of the limit of ny. If send y goes to infinity. Okay. So the first theory, right, I want to show you is the following, right? So if you take the average, if you take the average of the visit to y and first n steps, right? This is kind of the fraction of time of x spent on 1 to n, right? So this is the fraction of time of the Markov chain spent on first n step, right? So if y is recurrent, so this fraction, so actually goes to something, actually goes to something. So it goes to 1 over of the expectation. So this is the limit, right? This is the limit. You don't need to really to care this a lot, right? This makes perfect sense, right? So if ty, right, if you're starting from x, and ty is infinite, right? Definitely, right? This actually always equals to 0, right? So in that case, it's trivial. So if ty actually is finite, right? Ty is finite. Let's us starting from x. If ty is finite, then it visit. So then it visit y infinite times, right? So in that case, this actually just converge to the reciprocal of ey ty, right? It's 1 over ey ty. So right, as I said, right, so this is kind of average of waiting time, the average waiting time. So 1 over this average waiting time is kind of the is kind of the frequency, right? So as I said before, right, in master lecture, right, this is kind of the frequency spent and the state, right? And this is kind of the time average, right, fraction of time, right? This makes sense, right? This actually gives you kind of a stationary mirror, right? But this is more general, right, than previous theory. Okay, so this is a statement. It's a statement. So I will just briefly say the proof. You can check the proof later by details. But I want to be a bit fast so we can have more time on the main proof on the convergence theory. So how to prove this, right? How to prove this? So let's just let's first starting from y. So in this case, right? So this y, this can be general. This x can be general. But now let's starting from y, right? So x equals to y. So in this case, we define a sequence of random numbers. It's called RK. So K is okay. Those numbers, right? Those integers. So this is the time of case return to y. Right? So let's say originally, right? And time 0, right? You're starting from y. You're starting from y, and R1 is the first time you return to y, right? So this is the second time you return to y. Right? This is the third time you return to y. This is the case time you return to y. Okay. So of course, right? So if you take intermediate time, so T1, T2, T3, right? So this is the intermediate time. So it's the difference between K and RK plus 1. So TK means, right? For instance, TK means after you arrive Y and K minus 1 time, how long you need to wait before, right, the case return to y, right? So TK is the intermediate time, is the waiting time between K minus 1's arrival and K's arrival. Okay, so this is just convention, right? So by Markov property, so actually those intermediate times, T1, T2, T3, TK, it's an infinite sequence of random variables. So these random variables actually are IID, right? Because condition on the, let's say, second visits to Y, right? So this number of time are IID, right? Those waiting time are IID. Okay. So of course you can just write RK, just write RK and the sum of those IID random variables. So by strong law or large number, right? By strong law or large number, so RK over K, you can just goes to EY, TY, right? So here, right? So here, right, even this is infinite is true. Right? It really doesn't matter, right? Even this is infinite. Strong law of large number is still true. You can, if you're not clear, you can go through the chapter 3 for detail, maybe chapter 2 for details. So, but anyway, by strong law of large number, so RK over K converges to this, and this holds true almost surely. Okay. So, but you see, if you compare this term and this term, right, they are a little bit different, right? But they are not very different. So we can kind of, so this fraction, right, this average, kind of just this, right, up to like some small terms. So we just treat this. So how to see, right? How to see that? So let's say, right, you can think this as K, right? You can think this as K, and this is K, right? But this K is random variable, right? It's not if you fix the trajectory, you can think K is just a integer. Okay. So we can, so a priori, right, by the definition, so we know, so R of this number, so we know, right, we have this inequality. We have this inequality. So Y, right? So because R and Y denotes, so R and Y, right, R and Y denotes the number of visits by time n, right? So this is the first time n. Okay, so this number n and Y equals to the number of visits and time n. So let's say it's k, right? So it visits Y and in these particular times. So this equals to k. So of course, right? So you fix k and you see. So the first time it visit, what's the first time it visit y k times, right? If this is k, and then according to the definition of rk, right? We know so this should be n minus one, right? In this particular scenario. So of course this is less than or equal to n, right? And if you choose this as k plus one, right, so then it should be at least n plus one, right? So let's say in this particular is n plus two, right? So in this case, right, so of course, if you see the first time and the process, the stochastic process visit y for k plus one's time, so it should be bigger than n, right? So this is a basic inequality, right? And we use to estimate. Okay, so then, right, using the inequality star, we have this inequality, right? We just divide by ny, right? Just divide by ny, right? So here these two can cancel, right? These two can cancel, right? So it's exactly this inequality. Okay, by previous strong law of large number, right? We know, right? This part converges to the expectation. And this part converges to the expectation as well, right? And this converges to one, right? Since as n goes to infinity, right? Ny goes to infinity as well, right? Since y is recurrent. So by squeezing, right? By squeezing theory, so this part converges to the expectation almost truly as well. It's not very hard, but since here there's a little bit tricky, right? The tricky part is okay. So this is also random variable, right? This is also random variable, right? So there's a little bit tricky part you need to think of. But anyway, so we can get this, right? We can get our theory. If you just take the inverse, right? Take the inverse, you get our theory. You get this theory, right? So you just take the opposite, right? Take the opposite. Take the reciprocal. Then you converge to this, right? Okay. So this is the easiest part, right? The easiest part, given you're starting from x, right? First starting from y, right? Starting from y. Okay. So this is what we get, right? So this is what we get, right? If you're starting from y, right? So we get this. You get this. Okay. So how about the general case, right? General case is actually the same. It's almost the same. So why, right? It's a little bit tricky, right? But okay. So how to see that? How to see that? Okay. Okay. So we're starting from x, right? So x. But there are two parts, right? So if we're starting from x and we cannot go to y in finite time, right? So this is possible, right? So for instance, for instance, this is state 0, this is state 2, right? This is state 1. And it might have one half go here, right? It have one half go here, right? And it always go to itself. Of course, right? So this y, right? We choose y equals to 1. Right? This is a very particular Markov chain. So if you're starting from 0, right, you can never go to 1, right? So in this case, actually ty. So in this particular case, right, t0, you're starting from 0, and you go to right, go to 1. So in this particular case, actually, so t1 always equals to so t1 starting from x, x equals to 0. So this is always infinite. You cannot go to 1. Right? You cannot go to 1. So of course, right, if you cannot go to y starting from x, right, so that means the stopping time, the visit time to y is infinite. Right? In this case, if you just look at the first, the number of visits in the first n times is 0, right? So of course, in this case, it's trivial. It's trivial, and this explains why we put this here, why we put this part here. It's in the theory. So why we put this part, right? So if ty equals to infinite, right? So basically, right, this is all 0, and of course you convert to 0. Right? This is the trivial case. Okay. So so if ty is finite, right? If ty is finite, so if ty is finite, this means, okay, you can return to y, right? Condition on this, you can return to y in finite time, and we denote this finite time is just t1, right? Just t1. So R1 now again is the first visit to y, right? But you're starting from x, So x0 is 0, right? So, but once you reach R1, so then it's all the same as before. If you, let's say, and time R1, the Markov chain arrives y, right? So then you just keep revisiting y for many, many times, right? So then this is T2, right? The second visit to y, right? This is third visit to y as before. And the T2, 3 is the intermediate time, is the waiting time. Okay, so as before, right? As before, we know, right? So those, I mean, not T1, right? T1 is totally different, right? So T1 is different, but the T2, T3 are all IID, right? All IID, and actually they are. So actually they are. So they have the same distribution as before, as T2, T3 before, right? But you need this assumption, right? So otherwise, it's you should condition on you can first visit y, right, starting from x. Okay, so again, we can just compute this, right? Okay, we can just compute rk over k. This is t1 over k plus this term. For this term, we use exactly as before, right? Use the strong law large number. And for this part, right, almost surely, right, T1 is finite, but we send k goes to infinity, right? So this term actually goes to 0, almost surely, right? This is fine. This is almost surely finite, but k goes to infinity. Right? So for px, almost surely, right? We have rk over k converges to this. Okay. So this proves the theory, right? This proves all the theory. Let's let you see this part, right? So this actually basically tells us, right, the previous theory about how to represent the stationary distribution, right? So this is our representation, our previous stationary distribution. And this theory tells you, right, the frequency of visit to y can approximate the stationary distribution. I mean, if this is a stationary distribution, right? Okay. And you can starting from basically any point x, right? You can basically starting from any point x as long as y is recurrent. Okay. Yeah, if you have questions, just let me know. Okay. 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 So just a few comments, right? Um, just a few comments. This is a frequency, right, of visitor to Y, and this is the kind of the station distribution, right? I say kind of, but it's not necessarily is stationary distribution, right? But if it has a stationary distribution, it looks like this. Okay, so this theory can explain the name of positive recurrence, or now recurrence, right? Now recurrence. So positive recurrence means the expected so EY TY, right? This is the average stopping time, right? Average time you take to arrive Y. So if this is finite, right? So then this is positive, right? So positive recurrence means the frequency or the fraction of time you spend and Y is positive, right? So now recurrence means, right? So even it is recurrent, even Y is recurrent at the fraction of time, right? You probably have many states, and so it takes a lot of time, right? It takes a lot of time or steps to visit Y, right? And you just counting how many steps which you are and Y, right? In average sense, right, it's zero, right? So that's why it's called now recurrent. Okay, so it's just a name, and also, right, we can have a very natural corollary. We can have a natural corollary by dominated convergence theory. But actually, it's not it's bounded convergence theory. It's bounded convergence theory, but it's also a big dominated convergence theory. So a priori, right? This is just the frequency, right? This is just a frequency. This is just a frequency. So of course we know we know this is bounded, right, by one and bounded from below by zero. So and we know the convergence of this by previous theory. This is almost surely convergence. So if we, okay, starting from X, right, this converge in PX almost surely, right? So we can send this to limit in expectation, right? So we just write this, right? So what we have, right, and we write this out, explicitly out. I should write here is N, right? So it's a typo. Okay. So if we send N goes to infinity, this is the average. So this is the average, right? So then we have convergence. But this convergence, right? This is not. So this is not a Pnxy converge to something, right? But instead, it's the average of Pn. Right? It's average of Pn, right? This is the average of the first n terms of Pn, and this always converge, right? This a priori converge to this. Of course, right? This is easier to have, right, than the convergence of the each term. Right? So the average convergence is a less restrictive, right? We have convergence of Pnxy, so definitely we have convergence of this. We have convergence of this. Okay, so the previous theory, right, by bounded convergence theory directly gives you this. And also, right, if Y is a transient, right? So if Y is a transient, this is infinite. If this is infinite, so the convergence, so this is zero, so the right-hand side will be zero. So in that case, this equals to zero. And of course, we know this is true, right? Because so each term here, right, if Y is recurrent, this converges to zero. So if you take the average, of course, it also goes to zero, right? So this formula, right, this formula star, right, actually is true for every case, for all case, Okay. So usually, right, when we have convergence in this sense, So if we have convergence in this sense, so we say it converges in sense of Cesaro. This is in the average convergence. In the average convergence, you take the average of first n terms, then you have convergence. So if you in this sense, actually Pn, so Pn xy always converge, and we know the limit. Right? We know the limit is just rho xy over ey ty. We know, but this is in the Cesaro sense. So m equals to 1 to n. You take average, right? So the but even right. So as I said, right. So this Cesaro sense convergence, right? Convergence in Cesaro sense doesn't guarantee the converge of each term, right? So this for each term it might not converge, right? It's very easy to find the counter example. So as long as you have some kind of periodicity, periodic property, right? So then this might not converge. Okay. So why, right? So let's see a very easy example. Okay. So for this particular example, right? Let's say we have two states, A and B, right? And B. So this is the transition probability, right? From you starting from state A, right? If it's probability 1, you go to B. And if you are sitting in state B, right, given you have probability, you always go to A, right? So there are two states, right? Like rotating, right? Rotating. So we write the transition probability, right? It's P, right? So it's 0, 1, 1, 0. Right? If you take the square, you get P square. You get this, right? So you get identity matrix, and you keep doing this, right? So it's very easy to compute, right? So I mean, you don't need to compute, right? It's a kind of deterministic system. It's very easy, right? So PNAA, right, or PNABB, right, actually equals to 1, right? If n is even. So this equals 0 if n is odd, right? So if you look at this sequence of Pn XX, right, Pn XY, right? So this sequence becomes so first 0, 1, 0, 1, 0, 1, etc. Right? So of course, right, if you take average, right? So if you take an average of those sequence, you have convergence. But otherwise, right, this is not converge, right? So Pn not converge, of course, right? So actually, right, we can see, right, in the last theory we prove. So this type of periodicity, prevents the convergence, right? And this is the only reason it prevents the convergence of Pn xy. Okay. So if you know the Markov chain is not periodic, right? It's called aperiodic. Then you can hope to obtain the convergence of this Pn(xy). Right? So we hope to show this in the end converge. Hope to show this converge to pi xy as n goes to infinity. So this is a distribution. It's a distribution, a stationary distribution. Standard distribution. Okay, so any questions now? Okay, so if no questions, let's see the next. What M in F? M means, oh, okay, is that the index? Oh yeah, it's just the index. You're right. Yeah, it's just the index. So for instance, we have a sequence of a real. Okay. You have a. Yeah. Yeah, for instance, if you have a sequence, right, of numbers, right, it's a sequence of numbers, right? So there are two type of convergence, right? So maybe not two type, there are many type of convergence, right? So it just say two, right? So first, right, so if this converts to a number A, right? So this is a Euro sense, right? Second, right, this is easier to have. This is much easier to have. This converts to A. So this is a very popular. I mean, when you study the first course in analysis, you might have this problem, right? So if you have one, right? So one implies two, right? So but two does not implies one. So FM is just a sequence, right? So it's a function. It's a function depends on M. Depends on M. Okay, so I will keep going. So okay, I'm gonna keep going. So periodicity. So let's say, right, so X is right, let's consider S is a Markov chain, right, state for the Markov chain given a transition probability P. So X is recurrent, right? And we write all possible loop or possible lengths for loops starting and ends with X, right? So what does this mean, right? This means, right, if you're starting from X, you can return to X in finite time. You can return to X. But of course, right, P0 X right, is 1, right? So because, and so if you're starting at X, right? So in 0 step, you're always there, right? So here we need N is bigger than 1, right? Bigger than or equal to 1. So if you have this loop, right, if X, you have this type of loop. You have this type of loop. So definitely, so Ix equals to 1, right? So if Pxx bigger than 0, right? So then actually Ix equals to 1. Not just 1, right? So since now you can go from to X, right? In one step, right? You can keep doing this, right? You can keep doing this, right? So 2, 3, etc. So this is all natural number, all positive integers, right? All positive integers. So if you can go from X to X, you can go from X in any finite step, right? So but this probably not true, right? So this probably not true, right? This is a very particular case. So Ix is all the lengths of loops starting and ends with X, right? So you can go from X to X1, from X1 to X2, right? So then you go to X4 and you go back to X. So for this particular loop, right? So 1, 2, 3, 4, 5, right? So N equals to 5. So the length is 5. And we write every length as a set of Ix, and the set of Ix. Okay. So, and we call the period of X, d of X. So this is the greatest common divisor of dx. So I will give you an example shortly if you see that, right? So if X is, if dx equals to 1, if the greatest common divisor of the set is 1, so you can call Ix, you can call Ix co-prime, right? Co-prime. So that means greatest common divisor is 1. So we, in this case, we call X is aperiodic. So this means not periodic. Okay. So you know the meaning of greatest common divisor, right? So yeah, so this is so I think you know, and so let's give you an example, right? This example in the textbook, right? Here we have a chain. This chain is called I mean, you can call this square triangle. square triangle chain. So which means, right, you can go from 0 to 0 by following this square, right? Or you can go back to 0 by following this triangle. Right? So, and state 0, right, and state 0, you have equal probability going to -1 and 1. So then, right, if you add in state 1, right, you can only go to 2. If you add to 2, you can go to 3. You can only go to 3, right? Then you come back, right? It's the same as this loop. Okay. So in this case, I0, what is I0, right? I0 is all possible lengths of loop starting and ends with 0, right? Of course, right, so if you follow this one, right, you follow this loop, right, you get 4. You follow this loop, you get 3. And you can repeat this, right? You can here, then go from here to here, right? So we can write all these loops in form, right? 3a plus 4b, right? AB can be all positive integers, but they cannot be both 0, right? Cannot be both 0. Okay, so very easily we can write all the so I0, right? So all possible lengths from 0 and ends with 0 as I0, as 0. So I0 actually just 3a plus 4b, right? So we can write as something like which is span by 3 and span 3 and 4. But we should put this as intersection with positive integer, right? It's positive integer. So this is a set. This is a set generating by 3 and 4, but we only take the positive integer part. Positive integer part. Okay. So of course, right? Of course, actually d0 equals 1. Because 3 and 4 are co-prime, right? 3 and 4 are co-prime. So D0 equal to 1, right? So this is one example. So in this, right, so this 0 is aperiodic. Is aperiodic. So, I mean, so you can take as well, right? Since in the loop, right? So you can starting from -1, -2, or this as well, right? So 0 is aperiodic. Actually, all other points, all this, so this, right? All these are aperiodic. So in general, this is a so the period, right? The period is a class probability. So is a class property. So which basically means, right? So if dx, so if x is recurrent, right? Which basically means, right? If x is recurrent, I will just show you in next page. So, but basically says, right? So if from 0 you can go to -1, right? You can go to -1, and from -1 you can go to 0, right? And here really we only define period for recurrent state, right? So if this is recurrent, right? This is recurrent, and they are access from one to another, right? So then they share the same period. So their period should be equal. To put it more precise, we write in the following way. So we write in the following way. So if x is recurrent and y can be accessible from x, right? From x reach y, right? So then dx equals to dy, and dx equals to dy. So this is kind of, so this is basically the contagious property, right? So dx is a property of x. If y can be connected to x, so then they have the same number, then the same period. Okay. So another property is the following, right? There are two lemmas. I write it here, right? This is what we will use later. Two lemmas. First is the period is a class property, right? If 0, right? If 0 is aperiodic, and this chain is irreducible, right? Means any two states are accessible from each other, right? From each other. So then we call this chain, is aperiodic. Right? That means if you just pick any element in this chain, so dx, right? The period, right, is one, right? Is one. So if the period is one, we don't call it a periodic, aperiodic. Right? It's not periodic. Okay. So another property is this, right? So right, if dx equals to 1, right, if x is aperiodic, then so we can find a very large number. We can find an integer such that from this integer, so you can always go back to from x to x. So Pmxx is positive. So that means as long as m is large enough, right? So Pm, so xx, right, the diagonal. So the diagonal, so PMXX, right? So it's always positive when M is large enough. Right? This is actually, I mean, it's not very hard to prove, but kind of surprising. Yeah. So any questions now? So even though I will just prove these two properties, two lemmas. Okay. So let's first prove the contagious lemma, right? The class property lemma. Okay. So how to prove that, right? So this basically says, right, if x is recurrent, y is accessible from x, right? Y is accessible from x, then they share the same period. So how to show that, right? Okay. So since x and y, right, x is recurrent, right? So this is x. So y actually is recurrent, and from y you can reach x, right? So from y you can reach x. So you can choose a positive number k such that this is positive, right? From x you can reach y, right? So we can choose an integer l such that this is positive as well, right? So in particular, right, this tells you, right, from y to y, right, this is positive. Okay, so k plus l in particular should be one length, the loop y. So the period of y should divides, right? This is divides. So this means divides. So divides k plus l, right? So for instance, 2 divides 4, right? 3 divides 6, right? So this means 6 over 3, right, is an integer, right? So divides. Okay. Similarly, right, let's choose n, which is a length of a loop containing x, right? So in particular, right, so we have this, right? So same idea, right? So we can go from y to x in k step. We can go from x to x in n step, right? So then we go from x to y in l step, right? So we get p k plus n plus l is positive. Yeah, let's just delete everything, right? So then we get this is positive. You get, okay. So we get this is positive. So this means, right, so k plus n plus l is also a typical length, not a typical, it's a length of a loop containing y, right, containing y, right, this is a loop. So dy, right, so dy is this number, right, so this number. So what does this mean, right? So this means, so dy divides k plus l, dy also divides k plus n plus l, right? So dy should divide n, dy should divide n. And dx, right, dx is a common divisor of n. So dy divides n, right, for each n, right, in ix. So, and dx is the common divisor of ix, right? So dy should also divide the dx, right? So why this is, so dx is the greatest common divisor. Yeah, go ahead. No. So dx is the greatest common divisor of ix, right? So dx actually can, so let's say this set. So if you think this set is generating by several numbers L, right? So actually the greatest common divisor is a linear combination, it's an integer combination of those numbers by fundamental theory of algebra or something. Not algebra, not of arithmetic, not algebra. Uh, so dx can be written as a combination of m1 to ml. So of course, right? So if each dy divides m1 to ml, right? So we can get dy also divides dx. So that's what we can get, right? By symmetry, right? We can just get dx equals to dy. Okay. By symmetry, right? Because we can also get dy over dx. So in the end, right, we just get that because they are both positive integers, right? They're both positive integers. So this shows like the period is a class property, right? If two states are accessible, then they share the same period, right? So, and this really makes sense, right? This really makes sense. The second property lemma 2 is the following, right? So if x is aperiodic, so then as long as m is large enough, so it's always positive. PMXS is always positive. So probably I won't show details, right? Because we probably don't have enough time. But the idea is very simple. Right? The idea is very simple. It's the following, right? So let's say if 3 is in the loop, right? In 3 is the one length of the loop, right? 3 is there, 4 is there, right? So 2, 3 is just 6, right? Is there, 6 is there, right? So 8 is there, right? So because 2 4, right, equals to 8, right? So 9 is there because 3, if you take a 3 for 3 times, triple times, right? So you get 9. So actually, once you have two consecutive integers, right? Here is 8 and 9, you can doing this forever. And you can keep doing this, and you can show so they have consecutive so you can show like as long m is large enough, so every integers is in ix. Okay, so I mean this is just an example, right? So it's not a from here, right? So 8 and 9 is there. Then after it, actually every integer is in ix. But this is probably not true for others, but this ideas works for general cases. I want to probably, so this is a short, is idea of the proof, basic idea of the proof. Okay, so to do that, there are two steps. So as I said, right? So we can write this ix generating by L integers. And we know these integers are co-prime, right? So that's why since so they are co-prime, so dx equals 1 because the x is aperiodic. So we can, so by, so I'm not sure, right? So it's called, so this is, I think this should be called Euclidean something, Euclidean algorithm something. If you learn a little bit number theory, you know this. So it's like if M1, M2, ML are co-prime, right? So we can write one as a linear combination of M1, M2 to ML, and this A1 to AL are integer. I mean, they can be negative, right? And some of them must be negative because one is the smallest, right? But yeah, the good part is the following. The good part is the following, right? So A1, A2, right? So we write, so this A1 as a positive part minus negative part, right? And it's the same. So we can write, if we just regroup those numbers, right? We can write, so this actually is in Ix, right? And this is also in Ix. So from this basic observation, we know there exists one k. There exists a k such that k and k plus one are both there. Okay. So since k and k plus one are both there, we can iterate, right? We can just iteration, right? We just do iteration. I mean, it's called iteration, but it's just a basic observation. Since k is there, right? So 2k is there, right? We just take 2k, right? So we take the product of 2, we get this, or we get 2 copy of the k plus 1, we get that, right? So you can keep doing this, right? And you can show 3k there, right? These are all there, right? So if you do this for the k times, right? K times. So we can get, and plus 1 step, so everything is connected, right? So okay, so the last one here is k plus minus 1, and the first number here is k squared. So you can keep doing this. So everything is connected, right? So everything is connected. This shows the lemma two. So if x is aperiodic, so you can find a large number, or m0, such that pmxx is bigger than 0. So as long as m is big enough. Okay. So these two basic properties, we will use this to show the convergence theory, right? This is our main theory, right? So this is our main theory. And so this is the last theory I want to show, right, in this chapter. Okay. Okay. So any questions before we do that? Okay. So let's just state this theory. Let's just state this theory. Okay, what does this theory say, right? So if P is irreducible, so P is irreducible, right? It means, okay, first we have state space, and P is a transition probability, right? Transition probability. So let's assume this Markov chain has a stationary distribution. So since P is irreducible, right, and it has a stationary distribution. So from the discussion in last lecture, so actually we can represent this distribution pi x. So for each x in the state space is positive. So actually EXTX, right, is finite, right? So each x is a positive recurrent. Is recurrent, right? And this stationary distribution is also unique, and because it has the representation already. So in this case, no matter no matter what x is, so as n goes to infinity, you always approximate, right? So Pn xy always approximate pi y, always approximate pi y. So as I said, right, so let's just see one example, right? Let's just see one example. So this is our previous example. You can compute this example by yourself. 0, 2, 0, 8. So this is, let's call this matrix P, the transition matrix. So basically says you have two states, right? So this state is rainy. This state is sunny. So if today is raining, right, so then there are 0.8 probability it will be sunny tomorrow. And I might be wrong, right? So it might be not empirical, right? It's not maybe not true, right, in practice, but it might be true in some places in the world. Okay, I think it might be wrong, right? I should change this, right? It is, okay, I think this is some. Yeah, anyway. Okay, so here, right, you can compute, right, there exist, so this case, right, so this case satisfies all the assumption in theory, right? Why, right? Of course, it's irreducible, right? So from, so two states, right, A, B, there are two states, A and B, right? From A, you can reach B, right? From B, you can reach B, right? And it's not a periodic. It's definitely not periodic, right? So since Pxx is bigger than 0, right? It's not is Ax x which can be A and B, right? So is a periodic. And you can compute the stationary distribution, right? Pi equals to pi, right? Pi times p equals to pi. So how to compute this, right? You just take the identity matrix minus p, right? You know this very well. Right? So let's say it's a pi 0, pi 1, right? So 1 minus this, you get 0.5, right? You got a 0.5. And here is, so I might be wrong, but let me try. So it might be wrong. So, okay. Yeah, it's weird, right?
Hey, Zenfu.
Yeah, go ahead.
The identity minus P shouldn't decrease from the off-diagonal terms. Like you only subtract the. Oh no, yeah, it's right. Yeah, my.
Yeah, it's right.
Yeah,
Yeah,
it's
it's
right.
right. But so I see some. Yeah, so this equals to 0, right? Okay. Yeah. So I think I'm right. But this might be
Yeah.
not the I said in previous. So let's say. So this is 4, right? Plus minus so equals to 1 pi 0 pi 1 times 1/2, right? So and also pi 0 plus pi 1 equals to 1. Yeah, so this is so pi 0 over pi 1 equals to 1/2 times this. Right. So pi 0 might be this. So pi 1 might be this. Yeah, I might using different model, but okay, this should be true. So this is a way to write to find the distribution. Right? It's just the eigenvalue decomposition of this p. Right? It's one eigenvalue. The one eigenvalue is 1, and pi is just eigenvector. Right? It's the left eigenvector. And this theory tells you, right, as n goes to infinity, right? So the n, right, the nth iteration, right, nth power of p. So actually, we converge to this pi, 0, pi 1, pi 0, pi 1. So this theory tells you, right, if you just put in the linear algebra setting, right, then it's Markov chain with finite state. Okay, the finite state. So I might have made a mix, but yeah. Okay. Anyway, it's true, right? Yeah, because since my memory doesn't agree with this, so I might use different models. But anyway, so really doesn't matter. So let's tell you the basic proof of this theory. We only have 12 minutes, so we probably cannot go detail, but I can tell you the main idea. It's just 2 pages. Okay. Okay. So how to do this? How to prove this, right? The idea is something like this, right? So we want to mirror the distance between Pnxy and Py, right? So there's a possible way, right? So the following method is called method. So it's like this, right? So you want to measure the distance between Pnxy and Py. So one idea is write this as a distribution, as a transition probability, right? And certain probability of a Markov chain, right? This actually really means, right, starting from x and this x and y, right? So you can write the first term as, you're starting from x and you reach y and n step. And pi is the standard distribution, right? So pi y actually equals to y and equals to y, right? So if you're starting from this stationary distribution, right? So this term is the p y n equals to y. If you're starting from stationary distribution, right? Then to measure the difference of these two, right, it's kind of measure the distance between two processes, right? Xn and yn. So this xn and yn actually have exactly the same distribution, right? If you give them the same you give the same initial measure. But here we choose xnx, right? Xn start from x, and yn, right? We give them initial distribution as stationary one. So and each step, right? So actually they're same. So we are able to just to compute the difference between these two, between xn and yn. Okay, you will see the basic idea, right, shortly. Right? Okay, so let's first state the basic idea. Right? So we construct a priori, right? So in the very beginning, right? So the setting is we have a Markov chain, SP, and this Markov chain is irreducible, right? And each state is recurrent, right? We assume everything good, right? Yet, so each state, so actually is positive recurrent. It's not just recurrent, it's positive recurrent. Okay, from SP, we construct a tensor product. So it, like this, right? So we can see S2, right? S2 is the S cross S. And P bar is just a tensor product of the transition probability P. So you're going from x1, y1, you're going from x1, y1 to x2, y2. So what's the transition probability, right? So the transition probability is just, okay, you take the product. So first go from x1 to x2, then go from y1 to y2, and they are independent. Right? So they are independent. So we can, using the assumption, the Markov is aperiodic, we can show. So this new constructed Markov chain is also irreducible, and we have the station distribution, which is just the tensor product of the just the pi square, the tensor product of the previous stationary distribution, which means this pi, if we have two state A, B, right? So it just equals pi A times pi B, right? It's the tensor product. And each state, right? Each state is also recurrent and also positive recurrent. Okay, you can check step one. Step one is basically checking by aperiodic property. Okay, so the second step is just observation, right? So let's say if we're starting from, this is xn, right? This is yn. They might starting from different distribution or different initial state, right? But okay, so they can go something like this, right? So then y can go something like this. Okay, and we write this is the first time they collide. Okay, so the observation is the following: once they collide, we cannot really distinguish them, right? Once they collide, because this is a Markov chain. So this is xn, right? It's the trajectory of xn, this is the trajectory of yn. But they might collide, or actually, so this is a very likely event. They might collide, and after they collide, we cannot really distinguish them. Right? Once they collide, they are the same, right? Because it's a Markov chain, right? So we use this observation. So yeah. So basically, why this theory can be true, right? Why we can have lose our memory of initial state property is basically because this is a recurrent Markov chain. So if you're starting from two different states, right, in the end, right, they will collide. And once they collide, the history really doesn't matter. That's why. So it really doesn't depend on the initial state. Okay, to make this rigorous, right? So to write this in mathematical way, right? So we do the following observation, and this is really the key of this proof, right? So let's say, right? Let's say if we condition on this event, right? The first time the two processes collide. Well, let's say they collide before time n. So if they collide before time n, then at time n, they have the same distribution. Okay, condition on the collision happens before time n. So then at time n, they have the same. So how to do this, right? We just computing the following probability. Okay, so we compute this. We just extending everything according to value of stopping time, right? So t equals to m, and we sum up all possibilities of the value of xm, right? So xm equals to x, and we sum up with x. Okay, and we can write this as a conditional probability, right? So this is a conditional probability. And this step, right, really t equals to m, xm equals to x, then you condition, then you get this, right? But this is a Markov chain, so we only need to condition on the state of x, right? So the history really doesn't matter. And so condition on xm equals to x, right? So they follow the same distribution, the same transition probability, right? So this transition probability actually equals 1 by y, right? And this is the same, right? So if this t is the collision time, right? T is the collision time, and the collision time xm equals to ym, right? So if xm equals to x, of course, right? This term equals to this term. So anyway, so by this checking, we can show, right, if the collision happens before time n, collision happens before time n, so this property, right, equal to this property. Right? And basically says condition on t, the collision happens before n, so xn and yn have the same distribution. Okay, so this is the key. So this is the key part. Right, this key part. So using this observation, we can almost conclude, right? Let's using this observation and write a distribution of xn and time n. Right? So we just extend this event. We just expand this event. So they have two parts, right? So first part is this, right? So t less than n, right? Xn equals to y. The collision happens before n, right? Which is just this term. Or xn equals to y, but the collision happens after step n, right? So we can just using trivial estimate or trivial bound, right? So condition on this, right, definitely greater than that, right? So this is just equal. Right? So So xn and yn are symmetric, right? So this whole rule, if you exchange the rule of xn and yn, right? So then we can have the absolute value here. We can have the absolute value here, and this term comes from here, and this term comes from another, right? So if you change xn and yn. Right? So anyway, so if we sum up with the all possible choice of y, we sum up with all possible choice of the state y, so then we can estimate this, right? So we can ignore this, and just get not ignore because we sum up, right? We just get this, okay. So then we just using our choice, right? So let's choose initially, right, the Markov chain xn start from the one single state x, and y0 starting from a stationary distribution, right? Y0, the law of y0 satisfies a stationary distribution. So so yn also satisfies the stationary distribution, and in particular, just equals to y pi y. And this term, right, this term is just given by Pn xy, right? So we get result. We get the result, right? So since we get the estimate, which basically means so Pn xy and the stationary distribution converge in the total variation form. So here the convergence of this term basically because T is finite. Because T is finite, almost surely, right? So if we send n goes to infinity, we are done. Okay, so this is I actually basically tells you everything. The only thing not make fully rigorous, right, is this step, but you can check the by yourself, right? Just checking by a periodic property. Okay. So let's just go back one step, right? So it's called convergence theory. So it's Pn xy converge to a stationary mirror. So once you have the chain, the Markov chain is irreducible, and each state is not periodic, aperiodic. So then we will have the convergence theory. I will just stop here. If you have a question, I can answer. So from Wednesday, we will go to Brownian motion. So chapter 7. Basically, just cover all in chapter 7. And if we have time, we might mention a little bit about multi-dimensional Brownian motion, right? The relation with PD. But we only have 5 lectures. Probably we don't have time. So maybe I just spend one lecture on one section in Brownian motion chapter. So we definitely spend some time on E2 formula, because if you want to do some continuous probability, so that's the basic truth. But this course is mostly focused on the discrete ones. So yeah, probably we don't have time on stochastic differential equation. Okay, so I will stop here. If you have questions, we can discuss. Okay, yeah, thanks. Yeah, any questions? Yeah, you can unmute yourself and say, or in the chat.